Hello, this session is for some engineers who are newly attempting to predict the fatigue life of structures which are subjected to both constant and fluctuating loads. The fatigue analysis of a structure which are subjected only to fluctuating load is kind of straightforward, which is dealt in many textbooks and examples are also available from software. When the structure is subjected to a portion of a load which is not fluctuating and some portion of a load which are fluctuating, the analysis become little tricky. And moreover, when the induced stress on the structure is less than the yield limit of the material, then we can handle this using SN fatigue analysis methodology. But when the stress state exceeds the yield strength of the material, then doing a fatigue analysis using SN fatigue analysis procedure may not result in correct result, so we have to go for EN fatigue analysis. When the structure is experiencing both constant stress state due to the constant load and fluctuating stress state due to fluctuating loads, then this loading is called non-proportional loading. When the induced stress is less than the yield strength of the material, then we can handle this problem using Ansys workbench fatigue tool. An example is available in Ansys customer portal under knowledge resource solution. Search for solution number 2055951. In this session, I will majorly focus on a scenario where the stress exceeds the yield strength of the material. So we have to go for EN fatigue approach. As of April 2021, Ansys Workbench Fatigue tool cannot handle this scenario of non-proportional loading under EN fatigue analysis. So one have to use Ansys nCode design life product to carry out this particular analysis. In this session, I will demonstrate the typical procedure to handle both constant and fluctuating loads and how to do a sanity check on the results that we get from Ansys nCode design life tool, and I will also demonstrate an example of a practical scenario of a flanged joint connected through bolts. These bolts are preloaded. The preload on the bolt is kind of constant, it is not varying with time, but the fluid which is flowing through this flanged joint is fluctuating due to the operational condition. The pressure inside the pipe, when the machine is not operational, there won't be any pressure. As the machine is started, the pressure will rise and it reach the maximum value. Then during the shutdown of the machine, the pressure will come back to zero. Then during next operational cycle, again the pressure will rise and again it is going to come down during the next shutdown. So this load, pressure load is fluctuating, but the bolt preload is constant. So we will consider this as an example. Some of the points that I describe in this session may not be mathematically correct, but I want to make it more intuitive for the beginners to get hold on this. To start with, let's consider a cube of material which is subjected to a static pressure of 100 MPa like this, so that this entire body will develop a stress of 100 MPa in this. So if this is a static load, if I kind of draw this against time, this stress is going to be constant 100 MPa over time, 100 MPa over time.
Yes, over time.
Then on top of this, there is a 200 MPa fluctuating stress, or the pressure is fluctuating on this face. So this is going to produce 200 MPa fluctuating stress on this body. This fluctuating stress can be of two forms. One which can go positive and negative like this. So this is plus 200 MPa stress, and it can go to minus 200 MPa. The another possibility is that this is called a fully reversed loading. The another possibility is that it is a zero-based reverse loading. It will go to, the pressure will rise from 0 to 200, then come back to 0. Then again it will rise to 200 and come back to 0, and it will keep going like this. So in this case, the max stress is 200 MPa and minimum stress is 0. This is the scenario we are going to handle today. To demonstrate this problem, I'm setting up a new workbench project. I'm going to create a cube of material. For demonstration purpose, let me just take 100 by 100 cube.
Okay.
This is also 100. Then I'm connecting this to a static structural analysis. I'm going to save this project. And I will open the model and set up the boundary conditions. So this is kind of uniaxial loading. It means that whenever this pressure I'm talking about, this is acting in equal and opposite direction. So in order to set up the appropriate boundary condition, what I will do is that I will use the frictionless support on the bottom faces and the three faces, so that it will deform only in the axial direction. So here I'm going to apply a frictionless support on three faces, one on the bottom and one on the side and one on the back face, so that the model is fully constrained. And I'm going to apply a pressure on this face, which is 100 MPa. I'm going to, when we say the pressure is positive, it will act inside. This will become a compressive. So in order to make it tensile, I will make negative. And also I need to, this is applied on the default surface effect element. I want to also apply 200 MPa pressure, which is kind of fluctuating. Now, what would happen is that if we apply two pressure on the same location, it will kind of a supersede. Only this 200 is going to act, but we want both acting together, so that the first pressure is applied through the surface effect element. The second pressure I'm not going to apply through surface effect elements, but I will apply directly on the FE model, so that both will exist. Now I want to solve this as two load cases. Totally, I need two load cases. In the first load case, the pressure is, this static pressure is going to act at the initial and in the second load case also. But this fluctuating pressure acting only in the second load case. In first load case, it's kind of a 0. So this is, I'm kind of pulling this one side. I'm going to demonstrate both the scenario. How can we handle the fully reversed loading and also the zero-based reverse loading? For fully reversed loading, we need to reverse the pressure direction as well. So totally, I'm going to have three load steps now. In the first load step, the static load will be acting throughout the analysis period. And okay, I don't need actually actually 3. I think 2 is enough because this pressure is trying to pull outside, and in the third load step, it will be trying to push it inside.
Push it inside.
Okay, now I'm going to finally look at the axial deformation and look at stresses like equivalent one measure stress. I'll be looking at this in 3 time points: at end of the time 1, and at end of time 2, and end of time 3. In all 3 steps I will be looking at. We can have even the 1 element size, but I'm going to have 4 elements on this. So I'm just selecting all the edges. I'm saying number of element divisions, 2 elements. Okay, you can even solve this problem using 1 element. Now let's solve this problem. It's going to be pretty quick because the number of element size is really small, so that I can demonstrate all these concepts. So in the meantime, let's look at some of the hand calculations for this problem. So this problem, I have 2 sheets. One, we are going to talk about the fully reversed scenario where my mean stress is 100, but my max fluctuating stress is plus 200 and minimum fluctuating stress is minus 200, right? Then what I'm going to do is my total maximum stress. See, at any point of time, this 100 is also acting and this 200 is acting. At any point of time, my total maximum stress is 200 plus 100. My minimum maximum stress is 200 minus 200. Okay, that's the scenario we are going to handle that. Now we have solved this problem. Let's look at the stress in this body at the end of time 1. It is just axially deforming. Okay, like what you are seeing here. It is just axially deforming. That's the way we set up the boundary condition. At the end of time 1, we are seeing 100 MPa. At the end of time 2, we are seeing 200 MPa. This is 100 MPa static plus 200 MPa fluctuating stress. At the end of 3, we are going to see only 100.
Yeah, because it is compressive.
Yes, so we are going to see 100. Let me come back here. This is 200 minus, yeah, so this is going to be 100. Now let's look at this problem. Having done that, now if you want to do a fatigue analysis of this further in nCode, by default we are using the material library which is coming with Ansys. Instead, I think I have to go to a nCode folder where the installation is. I'm using 2020 R2. I'm going inside this, then GlyphWorks, then I'm going into material library. Yeah, this is the file. nCode mat XML is the one I need to import. To do this, I'm going to my project setup, engineering data. I'm going to import a new library. We need to click on this engineering data source. Then we have to add a new library. Double click, browse to this location to browse to the XML file. Go to this particular installation directory where you can find nCode mat XML. Okay, so once we say OK to this, we will get a new library for this one, where we have a lot of materials with both SN curve and EN curve available. So I'm going to use a material which is, for example, assume that this is made up of AASI 1020 steel. So what I'm going to do, I will then, once this library is ordered, click on this library. Then it is going to show all the materials inside this library, something like this. I'm going to choose a material, AISI, but depending on your actual material data, you can choose whatever material you want to use.
Okay.
Let me choose AASI 1020. Once you select that material, click on this plus mark so that this material from the library is transferred to the current project. Okay. Once you click on this, a plus bookmark will appear. Then we don't need this library information anymore. We can switch off this engineering data source, but this material is ordered in the current project. But if we want this project, this material to appear here, by default, it don't appear here. What we need to do is we need to come back to the project and say refresh project. Once we say refresh project, this material will be available inside this mechanical model where we can choose, okay, this portion of your model is made up of that particular material. Now let's go and review what information we have about this model. This model is going to have the SN curve for this material, and it will have all material constants for the EN curve as well. So depending on
Elastic and
whether,
plastic.
yes, depending on whether we are going to do stress life fatigue or strain life fatigue, we need to provide either SN curve or EN curve. Material is having, I will just change my project units. I'm comfortable with MPA. This material is having the yield strength of 280 and a tensile ultimate of 416. So if we look at this project, at some point of time, as we have seen, the stress experienced by this material is 300 MPa, which is more than the material yield. So in this kind of a scenario, it is ideal to do a strain life based fatigue rather the stress life based fatigue. Okay, having this done, I'm going to we will resolve this problem. I'm going to solve this problem again with the new material that we assigned for this one. Even though when the material is not crossing the yield, still one can perform a EN analysis. Both the EN analysis and the SN analysis are going to give almost the similar results, though it will not give the exactly same result. The problem is that collecting the SN curve for any material is easy. It is easily available in the literature and there is a large database. But if you want to collect the material input for a EN curve, it is complicated process. So that is why many people, unless otherwise it is not necessary, or if the yield is the induced stress is not crossing the yield, they prefer to do a SN analysis.
Yes.
But in that situation, there is nothing wrong in carrying out a EN analysis, even though the stress is well within the yield limit of the material. Okay, all right. So now, having solved this problem with the correct material data, the next step is to do a fatigue analysis. For that, you need to have Ansys nCode installed on your machine. I will first demonstrate this with a SN approach. We need to drag and drop the nCode SN constant life here. Okay. So once we do that, we need to say update here. When we say update, it is not really going to resolve the problem, but it will prepare some files for nCode. Once this is done, then refresh this cell. Then we can right click and edit. Now this is going to open nCode GUI, but it will take the material and the result information for this model from Ansys. Okay. This entire complete setup is pre-built within Ansys. This nCode is not really a Ansys developed product. We have a partnership with HBK who develops this nCode software. One can buy nCode directly from the HBK company or from Ansys. The advantage with Ansys is that this the entire workflow is pre-built,
Okay.
and we can parameterize that. If you go and change any parameters, like if you parameterize your dimension or material, just by saying update the project, it is going to resolve the fatigue analysis as well, so that setting up a DOE and other things become easy. Okay, that is one of the unique advantage of buying Ansys nCode Design Life product from Ansys. Having done that, this is the input file, which will already carry one file. This is nothing but it is going to have all the results coming from Ansys mechanical RST file. Here we can go and see the result cases. For example, I'm looking at my result from time 1 measure stress. It is going to show 100 MPa. We can look at case 2. This will show 300 MPa, and case 3, which is going to show again 100 MPa. Okay, so all the results have come in. Now, another important thing to do is that right click on the stress life analysis and edit material mapping and say yes. No, do we want to read the information from the other glyphs? Say yes. Now, what it is going to do is, by default, it will transfer that AASI material which we assigned in Workbench into nCode. Here we can go and view the material SN curve, because this case it's a SN analysis. Okay, then by default this material is assigned to material 1 of Ansys. This is done. The second part is the load mapping. Just say yes. When we do the load mapping, by default all the 3 load case results are available here. But in order to solve both static and the fluctuating load, we have to choose loading type as time step. Okay, we have to choose this as a time step. And now what we are doing is we are having all the 3 load cases. In this case, what it is going to do at every point, let's assume this is a time. In this fatigue, we are not really bothered about a time. Something like for a representative purpose, I'm saying a time. We have 3 load cases. In the first load case, the stress is 100. In the second load case, the stress goes up to 300. Okay, and in the third load case, the stress comes down. Let me just make sure. 100. This is plus 200, 300. Okay, the stress comes back to 100. Okay, so it will use this as one fatigue cycle. After that, this same cycle will repeat multiple times. We have defined just one cycle. Now let's go and okay, this is kind of correctly mapped now. Now we can go and solve this problem. Before solving, as this is having a static mean stress, we have to set some kind of a mean stress correction theory. Say edit, advanced edit, and yes, here is the place. Based on what stress we have to calculate the fatigue lives or the stress range, whether it is shear stress or 1 measure stress, absolute max principle. Absolute max principle is default, but one can go and choose any stress based on the physics and the material science phenomena. And also for mean stress correction, I'm going to use a Goodman, but nCode offers variety of choices. I'm going to use Goodman for this case. And if we go to analysis group, since fatigue is a surface phenomena, in order to reduce the fatigue calculation time, by default, the fatigue calculation is done only on the surface nodes, not the interior nodes. But if anybody want to calculate for the interior nodes also, we can say surface only nodes to false, so that it will calculate for the entire model. Once this is set up, then we can solve this problem. It is going to carry out the fatigue calculation for every node. and it is going to give the result. This is the result item. We can go here and plot life. So in this case, it is going to show some stress value. You can also come and plot what is the max stress, minimum stress, and so on. See, if you look at the max stress, it is showing 300. But if you look somewhere interior, it is showing 0 stress. Okay, it doesn't mean in Ansys we have seen the interior is also having the stresses. Okay,
Yes,
it is
yes,
not
yes.
only the surface, it is a constant stress state. Since we have said process only the surface nodes, it will process only the surface nodes. Interior
Okay.
it will consider as 0. Okay, that's a
Uh,
one way. But if we go and set we want the interior nodes also, it will also show the constant stress
sure,
state.
that constant.
So here is the again the tabular representation of this information. Here we can see the max stress as 300 and min stress as minus 100. If we come back to our calculation, here we have seen our max stress as 300, min stress as 100. Then we can calculate what is the range. The range is nothing but max minus min by 2. And
Yes.
here in this problem, the mean stress is the max plus min by 2, that is this much.
Yeah.
And this is having a R ratio because the R ratio is nothing but min by max. So it is having a R ratio. This is a what this means is, if I just kind of go and show a graph here, basically any point in this model is experiencing a mean stress of 100 and a alternating stress of 200, which goes positive 200 to negative 200. Then if we add both the mean, if we add these two curves, then we are going to see another curve which is nothing but mean. Okay, let me say this is the mean, this is the
Okay.
fluctuating stress. The fluctuating stress will fluctuate in a sinusoidal form,
Fine.
and this is nothing but mean plus the fluctuating stress. These two components. This plus the fluctuating stress, so that will be something like this. So this is now going to going max up to 300 because this is 200 plus 100. Okay, and
Okay.
the other side it comes like this, but we can't use this straight away because our SN curve, the SN curve is derived from the experiment assuming the load is fully reversed.
Okay. Okay. Got it. Got it.
But in our actual case, the load is not fully reversed.
Fully
In
reversed.
our actual case, the maximum minimum are different, which is having a different R ratio. So we need to correct for that. That mean stress correction is called Goodman correction. So you can refer any book for what is the Goodman correction, which is function of the material ultimate stress as well. Okay, for this material, the ultimate stress, as we have seen here, the ultimate stress for ASI 21 is 416.
4 and 6.
So if we correct it, this is going to be 263.29. If we go back to the SN curve and look at somewhere close to 263, how many cycle it can withstand? It can withstand somewhere close to 1 e power 4. Now let's go back and see how much is the life. It is 1.23 e power 4. That's what we are seeing here. If we if we come and plot the exterior surface 1.234 e power 4, that exactly matches with this SN curve, right?
Yeah.
This is one way of validating this approach. The second one is that now let's say in this case what we have done, we have provided 3 inputs to encode from load case 1, 2 and 3, so that it will calculate the mean stress from this data. calculate the zero reverse loading, something like this. It is not fully reversed, but it is zero reversed. Now, in that case, what is going to happen is, but my max fluctuating stress is 200, but minimum it comes to zero. It is not minus 200 like in other case. Okay, now my max stress is 100 plus 200, and my minimum stress is 100 plus 0, which is very 100 only. Now, if we do the mean stress correction, my equivalent ultimate stress is going to be 192.59. For this 192.59, if I go and look at it, now it's supposed to, this is 1 e power 4, this is 1 e power 5. My life has to be more than 1 e power 5. Okay. So how do we set up, tell nCode that it is not a fully reversed loading, but it is only zero based reverse loading, that we have to remove this third load case. Select this third load case at time 3. If your project description is very long, you can use this description so that it cut down. I don't need to use this third load case, which is kind of a reverse loading. Now I'm going to use only 1 and 2. So now what Ansys will consider is that it will consider only this part and try to do that. After this 300, it will assume it comes back to 0, rather stopping at 100. Okay. Now, if we go and do this analysis, this is the only change, I repeat, to differentiate between the fully reverse loading and zero based reverse loading. We don't want to consider the stress that is coming due to the reverse loading. So now if we go and solve this problem, we can see that our life is 1.9 e power 5. If we compare this, it is at 163. This is 1 e power 5. This is 1.9, somewhere close to 2 e power 5. That's what we are seeing that matches with Ansys. And also we can go and look at this table. My max stress is kind of 100 and max stress is 300 and minimum stress is 100 here. Like in other case, when we had a fully reversed loading, we have seen that the max stress is 300, but min stress is minus 100. Okay, this makes the life different between the fully reversed loading and zero based reverse loading. Okay, I hope this gives you an idea of how to set up this problem based on the stress life analysis. Now let's look at a scenario. Again, I want to repeat here. Just because the max stress is 300 here, it doesn't mean the equivalent alternating stress is still below the yield. Okay, the yield of this material is somewhere around the yield of this material is 280, but the equivalent alternating stress is still below the yield. Okay, that is something we have to remember. The procedure for doing strain based fatigue for the same problem is almost the same. Instead of dragging and dropping a SN constant, we have to drag and drop a EN, nCode EN constant life here. So now just refresh this and open this project. Now it is going to open a new nCode GUI, but this time what we are going to see is that strain life analysis, unlike in the previous project where it was a stress life analysis. Okay, the procedure remains same. Right click, say advanced edit, and go and say what kind of a mean stress correction theory you want, what type of elastic plastic correction, whether Hoffman-Seeger or Neuber, what kind of a mean stress correction, and ensure the material mapping is correctly done. This is AISI. If we go and see the view, we can see the EN curve for EN curve for this particular material. Okay, go with the endurance stress. This is a strain amplitude versus number of cycles, or you can also see the elastic plastic lines with this. So once we say, it will show the elastic plastic curve and so on. Make sure you assign the correct material here, and then make sure we have correct load mapping done, edit load mapping, depending on the scenario, whether we want to solve a fully reversed or zero based reversed. We have to set a correct loading scenario, change this to time step, remove this auto configure. Then you can remove everything here. Just say for a I'm just going to set up this for a zero based reverse loading. So I'm taking only load case 1 and 2. I'm not taking load case 3. Then you just go and solve it. As simple as that. Okay, so now it calculated the life. We can go and see the life here. So let me go and plot the stress, the max stress and min stress. The max stress is 207. Okay, and why it is 207? Okay, because what's happening if we look at this material stress strain curve, this is my strain and this is my stress. The material actual stress strain curve is something like this. So this point is the yield stress, which is around 280. Okay, but what happened is that since we have done only the linear analysis without considering any plasticity model, the stress has gone up to 300 here. Okay, this is 300. This is not really the correct stress. So that's where the plasticity correction is coming into a picture. So when we do a plasticity correction, this stress value will come down. We can have two different types of mean stress correction here. I will show you here. We can do under the EN engine either Newberg plasticity correction or Hoffman-Seeger. For this problem, I will say no plasticity correction. Okay. Then I would expect the max stress to be 300, same like the SN analysis. Combined stress and strain. Okay. Edit load mapping. Okay, so we have to go for this only when we need to actually do a plasticity correction. Okay, again, the plasticity correction is applicable or kind of acceptable only when the stress in the model exceeds the elastic limit at a local region. Okay, like so, for example, let's look at this case. If we look at this particular scenario here, let me show here. This material, if 280 is the yield stress, probably there is only a small portion of the material that exceeds the 280. Otherwise, if I said this is 280, only this red color is above 280. My model is globally experiencing the stresses within the yield. Only a small region is locally exceeding the yield.
Yes.
Any type of a plasticity correction is valid only for such a scenario. If a model is grossly, the gross stress state is exceeding the yield, then the
Okay.
plasticity correction may not work. In this case, the entire model crossed 200.
Yes.
280 the yield stress. So doing any kind of a plasticity correction for this is really not valid. But however, in this case, I just wanted to demonstrate that process. If you want to, if you want to do the real plastic strain based fatigue analysis, then we should not use any plasticity correction. Instead, under analysis group, instead of using the stress, we have to use both the stress and strain, so that we have to carry out a nonlinear material analysis in Ansys mechanical, including some kind of plasticity material model, so that both the stress and plastic strain data will be processed for the fatigue calculation, which will not use any strain plastic strain correction algorithm. Okay, so here in this case we have to use some kind of a plastic correction algorithm. I'm going to use Neuber here. So the results may not be valid, but here I'm demonstrating how we can use this, under what circumstances this becomes applicable. Okay, that's the point I want to demonstrate here. Because of the plasticity correction, the stress comes even below the yield. As I said, this corrected stress value is not right. Okay, so in this case, if you want to actually think about it, the entire material crossed the entire material is yielded. This material cannot take any load. This 300 is practically not possible. Since for a demonstration purpose, I'm kind of showing this scenario. Then the procedure for doing a strain life analysis is like this. Now, having explained this and also shown the know how we can verify this calculation, I want to demonstrate some practical problem for this. For this problem, I'm going to take a flanged connection. Two flanges are connected through bolts. Let this open so that I can describe the problem statement, and further I can explain the problem setup. So in this problem, what we are going to do is the two flanges are connected by number of bolts, and the pipe flange is subjected to internal pressure. Here, the internal pressure is expected to fluctuate between 0 to max pressure. Okay, let's assume this is a kind of a boiler tubing, where the boiler, when the boiler is operated, the pressure rises, then it comes to 0. When the shutting down, then again the pressure goes up and again comes down, like that. There is no negative pressure getting created. That's the scenario we are going to tackle that. So this is the flange assembly. As you can see, the two pipe flanges are connected with together with 4 bolts as shown here. Since this is kind of a symmetric structure, I'm just going to take one quarter of the model, and here I have 2 flanges. Then to represent the symmetry, I'm using the cyclic symmetry. The low and high edges are set up. I'm not really going to discuss how to set up the cyclic symmetry for any model in Ansys. Having done this, this model is made up of 2 different materials. Let me explain this. Here, if I go, the pipe is made up of ASI 1020 steel, but the bolts in SAE 2010. But the material what I am using here may not be acceptable to the industry, but however, my intention is demonstrate how you can assign for your own material for different parts. As you see here, this bolt is assigned with chrome steel. The top flange and the bottom flange is assigned with AASI. Then this pipe, if I kind of consider this as a pipe with flanges here, two flanges connected using number of bolts at this side. Now what will happen? This pipe has to close somewhere, right? This pipe has to close somewhere. But we are not modeling the entire length. We are cutting this pipe at some distance like this. We are considering only this small portion. But this axial force due to the closure will always act here. Okay? That is the one scenario we need to consider. So when we think about loading for this problem, so we are assuming the one end is constrained, and this side, this tensile force is acting, trying to separate the two joints apart. That's the scenario we are considering. So the bottom is kind of constrained, and the bolt pretension load of 5,000 Newton is applied on this bolt. And in first load step, this 5,000 Newton is applied, and second load step, the bolt is locked. And then I have an internal pressure acting on the inside wall of the structure, and the pressure, the axial force to simulate the closure effect, the axial force is something like a 6,000. Again, I kind of repeat, the force value I'm using here and the bolt pretension may not physically make any sense in a practical scenario, but my objective here is to demonstrate and produce some kind of a meaningful stress and demonstrate this. This problem is set up in two load cases. In first load step, only the bolt load is acting. Both the pressure and force both will fluctuate, okay, as the fluid as the pipe is in operation. So in first load step there is no pressure, only bolt pretension. In second load step 20 MPa internal pressure acting, and also this axial force is due to the fluctuating pressure. So both will be are applied in the second load step. I solve this problem and I look at my stress state and so on. If you look only the bolt at the end of the preloading, the bolt is seeing 634 MPa stress. If you come back and see the material property of this chrome steel, the yield strength of this chrome steel is almost almost 2000 megapascal. So this is well within the limit. But the pipe is made up of ASI 1020, which is having the yield stress of 280. As we can see here in this model, at the end of bolt preloading itself, the material is going into some plastic zone. Okay, it goes above 280, but the one way to handle this properly is include some kind of a elastic plastic material model for this material and calculate the plastic strain, but that is time consuming analysis. So in order to save time, and we know that the plastic strain is locally, then probably it is acceptable to use some kind of a plastic strain correction. So we are still carrying out the materially linear analysis, though we are considering the geometric nonlinear analysis, considering large deflection on and so on. Okay, and as we can see here, the total stress is 850. The the pipe material experience 278 due to the bold loading. It is not crossing the yield, but when we apply the external load, pressure and axial force, it crosses the yield, it goes up to 380.
Slightly. Okay.
Yes, slightly, okay, not too much beyond that. And again, the bold is seeing 634, which is well below the bold material yield of 2000 MPa. Then after the loading, the stress slightly goes up on the bold as well. And the final thing I want to show is about 280 is this. And this problem is not very practical as such. Say, for example, if you look at this, the bolt configuration is not good enough to completely keep the joint the joint in a closed state. As you can see, the bolt joint will open up. Okay. But we are not really focusing on that. Our focus is only the fatigue analysis. Assume that the sealing and other things are taken care for this joint. There may be additional O-rings or gasket somewhere, but our objective is not that. Okay. So we are bothered only about the fatigue analysis, not bothered about the sealing effect and so on. So once we do this analysis using 2 steps, the next what we need to do is, as I demonstrated, we need to collect the SN or EN analysis. I have done this analysis. This is same as what I have demonstrated for the previous problem, exactly the same procedure. Once if we take the SN analysis procedure, let's go and look at the SN analysis procedure, how the results look like. I will close the other 2 nCode project which we already discussed. Okay, I have carried out this analysis. As you can see here, there are 2 materials. Material 1 corresponds to the bolt. It is automatically assigned with chrome steel, and material 2 and 3 corresponds to 2 pipe flanges. They are assigned with the AASI 1020. Once again, the load mapping also I will kind of explain. So we have solved this as a nonlinear analysis, right? Sometimes when we solve this as a nonlinear analysis, we may have to carry out multiple load steps, right? So we will see the results at 0.5, 1, 1.2, something like that. But what we are interested is at the end of bolt preload, at the end of the pressure. That's the 2 things. But all the results are going to come in here. But we have to choose here for the time step mapping. We have to use only time 1 and 2. We don't want to use this 0.5, or between this 1 and 2 also there may be hundreds of substeps exist. We don't want to really worry about that. For this we have to choose only time 1 and 2. Okay, this is a zero-based reversal. And if we go and look at after the calculation, what we are going to see is that after the mean stress adjustment and so on, my max stress is 418. Okay, this is much above the yield. So now what nCode is going to predict is that there will be a static failure at this location, because the stress goes something like 418, right, after the mean stress correction. So nCode will show at this location there is a static failure happens. This is kind of this is kind of okay in numerical point of view. This is where the static failure is going to happen. But practically this may not happen, because still there is a good amount of zone. If we come back here and look at take a cut section at this region, somewhere in this region, and let me just take a cut section at time 3. How much material goes beyond the yield? There is only a small portion of the thickness goes beyond the yield.
Yes, yes.
Okay, it doesn't mean it is going to fail here, but if at all this is the place where the crack is going to initiate due to a fatigue, that we can understand. But this doesn't mean a static failure, right? So if you do a SN analysis for this kind of a scenario where the stress exceeds the yield stress from a linear material analysis, then the SN analysis is going to over conservatively predict the results. That's what I wanted to explain here. But what we can do is that now let's look at if we set up the same problem.
So the thing is, so if the stress is in local region going beyond the yield, then if you do SN analysis, it will give more life cycle.
No, it will show less life cycle.
Okay.
The SN analysis showing it is a static failure. It means that it can't even withstand one cycle.
Okay. If EN analysis, what?
Next, I'm going to demonstrate the results for the same stress state from the EN analysis using plasticity correction method, rather using the plastic strain computed from Ansys FEA solver. The problem setup, everything is exactly the same as I explained in the previous problem. Use this mark to fit the model, and you can see that when we use the EN analysis, it predicts kind of a failure. Critical location starts somewhere here. That is correct. And also it says that it is not going to fail immediately. It can withstand 1.3 e power 6 cycles. Okay, this is something meaningful results what we can see considering the plasticity correction. And after the plasticity correction, the max stress comes to 323 and min stress is 26.3. This is little above the yield, but not too much like in the previous case. The important settings we need to do is map the loading correctly, depending on whether it is a fully reversed loading or it's a zero-based reverse loading. If you see your the description too long, use this.
How it is taking that first load step is constant and second load step is fluctuating?
It is not taking anything as constant and thing. In first load step, we have some stress state.
Yeah.
In second load step, we have some stress.
Okay.
It just uses these two stress and calculate what is the mean.
Okay, got it.
Okay, all right. So set the loading correctly. Use the stress state from appropriate time from Ansys mechanical FEA solver. And another thing is get into the advanced edit. Here you can choose what stress has to be used for all the calculation. You can choose the appropriate mean stress correction based on the theory. This is more of a theory, not more of a software point of view. Ansys provides these three methods. You can choose one of the thing, and also use a appropriate plasticity correction. Again, you can refer the fatigue textbooks and understand what is the logic beyond Hoffman-Seeger and Neuber, when what is applicable and so on. Okay, and we get a meaningful results like what we are seeing here. We have to rerun the whole scenario. I will run this case, and this is what I wanted to demonstrate today. If you have any system which consists of a constant load and a fluctuating load. In this case, it is a bolt preload which is constant. But it is applicable to any kind of a load, not necessarily a load. Like in the previous example, we have seen that you have a total load. In this total load can be visualized something like this. This is your force. 0, and your force is something vibrating like this. Then what you can think about is this is the mean load. About the mean, this much is the static load. Okay, about this static load, this much is the fluctuating load. Okay, those concepts can be used for any fatigue analysis purpose. This is coming from the two stress state. It is known. See, what we are providing to Sherlock is these two stresses at every node.
Yes.
Okay, this is at time 1, this is 100. At time 2, this is 300.
300, yeah.
And time 3, it is 0.
Yes.
From this, if you calculate what is the mean stress for this history of loading, you will see the mean stress coming correctly. We are not providing or we are not telling nCode that this is my static stress or this is my fluctuating stress. Providing the different stress state. In fact, if we go back and look at this, our fluctuating stress, as I explained, is only 200 MPa. But in none of the load case, none of the time point results, we have 200 MPa. Okay, if you look at, we solved it for 3 time points. In none of the time points, we are seeing plus 200 and minus 200 stress. The effect is taken care by looking at these 3 stress states. In this whole process, we are not really instructing nCode that this load is a static load and this load is a fluctuating load. The way it is done is it is something like this. If you kind of know two stress state, which is S max and S min. Okay, let's consider the another case. What we have given is for a zero reverse loading, we used two time points. In the first time point, we had a stress of 100. Yeah. In the second time point, we had a stress of 300.
Yes.
Right. So if you calculate what is the mean stress from these 2 points, this is mean stress is nothing but 100. The minimum, this is S min.
Yeah.
This is S max.
Yes.
So mean is nothing but S min plus S max by 2. So this is 100 plus 300 by 2. This is going to be 200.
Yeah. So
that is equivalent to how the theory calculates the mean stress. There is no need to explicitly tell this is static load, this is dynamic load. In fact, there is no stress state in our result file which has a 200 MPa stress, which is actually the fluctuating component of the stress. This is very important to understand how the mean is calculated and alternating is calculated from the given load mapping here. Okay, so there is a stress at every node from this point. There is a stress at every node from this result. From that it will calculate. So this is the example we have seen. We are kind of seeing the stress state and getting the corresponding fatigue life. I hope this session gives you some idea about how to set up the analysis using Ansys tools and how to do some kind of a basic sanity check. Finally, I want to show that once you get into Ansys Learning Hub, there is a dedicated course on introduction to Ansys Design Life, which will kind of help you to make familiar with the different procedures and the different terminologies of Ansys nCode Design Life product. Okay, with this I will close today. Thank you.